All right, so we're going to do a Riemann Sum review. And this is going to go over some of the material in 3.6, which is optional. And we'll back up and do a problem on improper reals. So let's consider f of x to be x squared plus 1. And let's look at the interval just from 0 to 2. And let's start off real easy with n equals 4. Let's do 4 subintervals. And let's start off with right endpoints. So notation for that would be an R with a 4, meaning use right endpoints, do 4 intervals. Okay. And we'll work up to some other ones today too. Good idea to start this is to sketch out your interval. Actually, I should put that down lower and sketch out the whole function with it. I'll do it down here. So let's see, I'm going from 0 to 2. 1 is in the middle, and then I should, since n is a small number, it's a good idea to draw out the partition. So we would have 1/2 there, 3/2 there, 1 in the middle. And let's see, what do we get for function values? We get 1 through 5. So 1, 2, 3, 4, 5. 1, so we have a point here. We have a point at 1, 2, right about there, and we have another point at 2. Oh, no, wait. Yeah, that's right. And then 2, 5, right? So here's my parabola kind of stretched out. And we're making these Riemann sums since we're doing right endpoints, and this function is increasing. That turns out to be an upper sum instead of a lower sum. Those are rectangles. Reminder about coming up with these values here. So this one was pretty easy. We take on delta x, for example. We take the width of the interval, which is just b minus a, and we divide by how many pieces we want in. So in this case, my b is 2, a is 0, divide by 4. I get 2/4 or 1/2 is my delta x. So then starting at that left endpoint, so in this case, that would be called x of 0 is always the left endpoint, and x for the subscript n is always the rightmost endpoint. And so to generate our x sub i's for right-hand endpoints, it's a matter of starting all the way over on the left. We usually call that number a. And then I add on a bunch of delta x's. How many delta x's? That many, whatever I happens to be at the time. So that's always the formula for right-hand endpoints. So in this case, my formula for right-hand endpoints would be a is 0, delta x is 1/2, multiplied by I. So the first one would be 1 times 1/2. The second one would be 2 times 1/2. The third one would be 3 times 1/2. And that should take me all the way to the nth one, 4 times 1/2. Starting to ring a bell? Okay, we did this a long time ago. So again, if n is small, it's not too bad. You can draw it out, you can see all the numbers. And for most of the homework problems in 3.6, it's not using right-hand endpoints, but the numbers are relatively small, so you can easily draw it out and see what all of them are. So in this case, if we continue, what does this look like? R sub 4 would be the sum as I goes from 1 to 4. of my function evaluated at those special numbers times whatever delta x is. So in order to fill out that sum, right, we have to first figure out, well, what the heck is delta x? And based on that, in the starting point and ending point, we have to say, okay, what's a formula for the x of i's? So we got that, and we just need to plug that stuff into the function. So I don't even have to do summation notation here, because I can pretty clearly see what each of these y values is according to the function. Right, but I'm going to do the summation notation and then just do it clean. So let's see, what do we have? We have the sum as I goes from 1 to 4. My function is something squared plus 1, right? And then I need to multiply that by delta x. What's my delta x here? 1/2. 1/2, so I throw 1/2 here. And what was my x of I?
1/2 I.
1/2 I. Right, is the conclusion we came to right there. And what happens if I start using this? Well, this summation notation says let I equal 1. So if I equals 1, I'm going to have 1/2 squared plus 1 is the first y value. Multiply that by 1/2. Add on. I jumps from 1 to 2. So that's going to give me 1/2 times 2, which is 1 squared plus 1. That's the y value multiplied by 1/2. Plug in 3. 3 times 1/2 would be 3/2. Square it, add 1. That's the y value. Go to next. Multiply by my delta x, 1/2. Last time, plug in 4. 4 times 1/2 is 2. Squared plus 1. Multiply by 1/2. You could have done each of these calculations ahead of time and then just plug those numbers in. Right, like maybe you're plotting those points on the graph. I had plotted each one. So what do we got? We had 1/2 squared plus 1. So we're going to have, I have a pen, yeah. So that's going to be 1 1/4 or 5/4 times 1/2. And then the next one we plugged in 1, which gives a y value of 2 times 1/2. And then we plugged in 3/2, which is what, 9/4. 13/4, is that right? Times 1/2, and then we plugged in 2. And we got 5 times 1/2. Let's see, did I do that 13/4 right?
I think so.
3/2 squared is 9/4 plus 1, so that'd be plus 4/4. 9 plus 4 on a good day is 13. Yeah, okay, I got it. All right, so it's not too bad. We could plug this into a calculator. Here I'm getting a fractional answer. So what do I get? Let's just finish this off. Probably could have factored out that 1/2 right away, huh? So just going back to the summation notation, what's the variable in the summation notation? I. Right, so this could be cleaned up quite a bit. So I'm going to play with that just to remind you about the rules for summations in a minute. But 1/2 is a constant multiple. That constant multiple could have been pulled out. Right, we'll go back and play with that in a second. So let's see, what do we have here? I can pull out the whole 1/2 all over the place. And then I just have to add up these other things. 5/4 and 2 and 13/4 and 5. Let's see, 13 plus 5 is what? 18. So I have 18/4 plus 7, and what's 18/4 would be what?
4.5.
4.5 plus 7, 11 and 11.5. So we get 1/2 of 11.5. Let's see, half 11 is 5.5. Half of a quarter is a quarter. So is that 5 3/4? Anyone plug that straight in the calculator? If that's what Cargo plugged it in. Yeah. So sometimes fun with fractions. So that's an estimate. Is it an overestimate, an underestimate? It's an overestimate, right? Because in this case, because the function was increasing, my rectangles were higher than the function. If we did a left point, endpoint, we did a lower estimate. All right, let's focus on the sum for a minute, and then we'll just do a couple other examples. So if I break down this sum, oops. So I have the sum as I goes from 1 to 4 of parentheses 1/2 I squared plus 1 times a half. I just want to play with this for a minute. So just think back to exam 1 when we had to set up a Riemann sum to take the limit. The half is a constant, so the half comes out. And then I get the sum of a sum.
I use the right one to work. Yeah, what do you do?
Oh my. I think I was thinking ahead to that 4 up there. I don't know what happened there. Brain-hand disconnect. Okay. So the sum can be broken up. I can kind of distribute it over the sum inside. You can't do that on a product, but you can for the sum and a sum, because it's just a whole bunch of addition problems. So this could be viewed as 1/2. Weird. I didn't see 1/2. 1/2, right, times the sum of the 1/2 I squareds, and then I'm just going to carry that 1/2 through as the sum of ones. And this over here I could break down even further because I could square the half and the I, because then this will be a constant multiple right there. So 1/2 squared is 1/4, and bringing that out times this half, I would have 1/8. Color 1/8, the sum of I squareds. And I have 1/2 times the sum of ones. Do you guys remember we had formulas for like?
What is
2I minus 1.
Oh, what's the formula for that?
Yeah, I know it.
Yeah, so the formula for the sum of the squareds, So just a reminder, let's see if I can get them right. The sum as you go up, as I goes from 1 to n of ones is just n. The sum as I goes from 1 to n of i's is n times n plus 1 over 2. The sum as I goes from 1 to n of I squareds is n times n plus 1 times 2n plus 1 over 6. Oh, can I get the i's to the third power right? I don't know if I can get that one right. Let's see. I'm going to guess. I think the sum of the cubes is n times n plus 1 squared over something. 8 or 12?
I think it's 4.
I think it's
6.
You think it's 6? I don't remember. I'm gonna have to look it up.
I remember. It's 4.
Was this? Where did I have this posted? I posted it somewhere. In my notes,
It's
didn't I?
n squared, n plus 1 squared over 4.
Oh, it's over 4. Who said that? You said that one? Nice.
That's also n squared. Did you get n squared?
Yeah,
Oh, no,
so
you
here's
did it.
my
Oh, yeah.
n squared. This is my n plus 1 squared. I just squared it in the numerator.
You have to square it.
It's on the outside.
The square of the 4 too?
No,
Oh.
it's the ends up. The square's on the outside.
Okay, I'm all right, right?
Yeah.
It's just a slightly different version of what you said.
Yeah.
Yeah. Okay. So I need this one here and that one there to do this. Okay. And we needed to do this if we wanted to take a limit. Now here we just plugged in 4, so there's no limits here because 4 is my endpoint, not some n way out there. Where are we going? Here. Okay. So what is I going up to? I is just going up to 4 here. So then this answer, according to that reducing sheet, should be 1/8 times, let's see, 4 times 5 times, let's see, 2 times 4 is 8, plus 1 is 9, over 6. That's that n plus 1 and 2n plus 1. N is 4?
N is 4. N is.
In this case, N is 4, yeah. And in the problem on the last test, the first test, N was N on part of it. And then I'm just going to have plus 1/2 of 4. All right, let's see. Does that give us the same answer we got before? Let's clean it up a little bit. 2 goes into 4 twice. So I have a 2 hanging out there. 4 goes into 8 twice. 3 goes into 9, and 3 goes into 6. I think that's all that comes up. So what's in the numerator there? 15/4 plus 2. 3, because what I have left here is I've got a 5 and a 3 in the top. Otherwise, I have 1s, and I just have 2 times 2 in the bottom. Yeah, so I think what we have using this version is 15/4 plus 2. 4 goes into 15. And 3/4 plus 2. Oh, that's not the same answer, is
It's
it?
not the same answer.
Oh, shit. What happened?
And this is what. No, it's just.
I got the
I
same
love
answer.
Riemann
It's 5 and 3
Sums.
quarters.
Oh, it is 5 and 3. That was what we got before?
Yeah.
Sorry, it was a long time ago. I forgot. Apparently. Oh, yeah, we got the same answer. Oof. Okay. So what was the point of all this? The point of all this is, what is an integral? An integral is this limit process for areas, where instead of saying n is 4, we let n be n. And we repeat this whole process. And then we get a whole bunch of things like this that we then have to break down into things like that. And hope we can take the limit as n goes to infinity. I'm going to skip that problem.
The first,
On
like,
the test?
on the first sum,
Maybe.
the top is just 1. What if I was like 3?
Then the 3 would be like a constant multiple, so it would be 3n. So more generally, if this was the sum as I goes from 1 to n of some constant, it's just that constant plus the constant plus the constant.
What if I equals instead of 1?
Oh, what if I didn't start at 1?
Oh, you
Then you have to figure out what's the distance from the lower bound to the upper bound.
So it's n minus 1.
So it would
Or
be
n minus
n
3.
minus 3. No, n minus 3 plus 1. Because if you think about it, here, if you did n minus 1, you actually have n of
Cancel? Wouldn't you be putting in?
Okay, so you were asking a different question. So this would be c times n. What Ben was asking is, what if the sum, instead of starting at 1, started at something like 3 and went up to whatever n was? So compare that to starting at 1 to n. The answer is n, right? Yeah. If you just take the top boundary and minus the bottom boundary, that just tells you how many spaces there are between 1 and n.
So it'd be n minus 2.
So, well, if it would be n minus 1 plus 1, because that would give me the n up there.
No, the
So up here, yeah, it would be n minus 3 plus 1, which ends up being n minus 2.
so that's like finding the areas between two things. So you take the top one and you find the area of that, then you have to subtract the bottom one.
Yeah, so like here I am at 1, and like maybe I want to jump all the way over here to say 8. We're ignoring the fact that to get from 0 to 1, there's a gap. If I take 8 minus 1, all that tells me is that there are 7 spaces, whole number spaces in between. Okay, it ignores this right there. So that's where the plus 1 comes from. That's one way to think about it. Okay. All right, so back here. So I like using right-hand endpoints because I think the formula works out nicer more often than left-hand endpoints. Okay? It works for me. But there are many other techniques, right? Before we took the right-hand sum and the left-hand sum and we averaged the two of them. Okay? And that's what like finding a midpoint instead. So we're going to do this again with what's called the midpoint rule. And then I'll show you what trapezoid and Simpsons rules are. I'm not going to really do them though. All right. Midpoint rule. Pretty simple. You just find the midpoint of each interval. And that's what you plug in. Could you create a general formula for this? Yeah, but it's a tiny bit messy. It's not too bad, but I'm just going to break this down for this example. So I'm going from 0 to 2, same as before. I'm going to let n equal 4. So that means I'm trying to find what's called capital M4, midpoint 4 intervals. So then I should also break down here and draw my subinterval divisions. And then I'm going to use the same function as before, f of x equals x squared plus 1. And then, let's see, 1, 2, 3, 4, 5. So I've got a point at 0, 1. I have a point at 1, 2. I have a point at 2, 5, somewhere over there. So here's my parabola. And the rectangles are exactly the same, sort of, in that they separate at each of those divisions, at 1/2, 1, 3/2, and 2. The difference is to get their height, I'm not going to use the right side or the left side. I'm going to find whatever number is in the middle. So in the middle here would be a quarter. Okay. How do I get that? Well, in general, you got to find delta x. Delta x, remember, is always a minus b over n. So for us, that's 2 minus 0 over 4, which is 1/2. And to get the first number that I would call x sub 1 for the midpoint, you just go to whatever your starting point is and move over by 1/2 of delta x. Why 1/2 of delta x? Because I want to end up in the middle of that first interval. That first interval has a width of whatever delta x is. So I'm going to evaluate this at a quarter.
Can you just add a quarter to a 1/2?
To continue, yeah, so then to continue, x2 is going to say, well, take whatever x1 was, and this time I'm just going to add delta x. Why just delta x? Because I need to get to the middle of the next interval, which is a whole delta x away now. So you do a 1/2 step at first, and then you do a full delta x step after that. So that's going to put us at 3/4 is what we would plug in there. And then I just keep jumping by delta x. So I add 2/4 to that. That's going to put me over here at 5/4. And then I add 1/2, which is 2/4. So that's going to put me over here at what? 7/4. And there's a nice pattern to that, right? The numerators are just odd numbers over 4 in this case. And then I'm just going to plug each of those in to figure out what's the height there. What's the height there? What's the height there? What's the height there? And so now these are my new rectangles. Now can you see how this is a slightly better estimate because I have both in the same rectangle an underestimate and an overestimate happening at the same time. Kyler?
What's the delta x? Is that 6 5 minus?
Right here?
Yeah.
That's
Delta
B
x in
minus
general is always b minus a. So
Oh,
b is
okay.
the right endpoint and a is the left endpoint.
Okay.
Yeah, so that's a b minus a. I'm just reminding you in general how you
Okay.
find delta x. And so now, just like before, we just plug those in and see what we get. So let's do it. Oop. It's not tracking good today. So M4 seems to be equal to, now what's delta x for every interval?
1/2.
I'm just going to pull it out front, okay? So I'm going to have 1/2 times the function value at each midpoint. The first midpoint was a quarter, so I'm going to have a quarter squared plus 1. And then the next y value is what? Well, I'll plug in the next x value. The next x value I think was 3/4 squared plus 1. And then the next y value. That was what, 5/4 squared plus 1. And finally the last one, which I believe was 7/4. Only difference between this version and the right endpoint is we just had to pick a slightly different x value each time, but it's the same routine, aside from figuring out what's the pattern for those x values. Who's fastest on the calculator? What do we get here? Let's see, GeoGebra. You already got it? Oh, 1/2 times. I'm going to try using the sum formula, maybe see if I can do that here. GeoGebra have a sum in it. Once, ooh, parentheses, and expression, yeah. So okay, so I'm going I from 1 to 4. What am I doing? Something like I over 4. Square that. I'm going to be the slowest one here. Parentheses, I over 4. Squared plus 1, and that's not really an I, it's really a 2I minus 1. 4.625? Is that right?
4 1/8.
4 5/8.
Oh yeah.
Unless I screwed it up.
That's what I got.
If I plug in I equals 1, that gives me 1. If I plug in I equals 2, that gives me 3. Yeah, that's the right formula. Yeah, so 2n minus 1 generates odd numbers. 2n would generate even numbers. Okay. So 4 5/8, 4.625. What did we get before? 5 3/4,
Yeah.
which was a definite overestimate, right? This one was kind of splitting the difference a little bit, so I don't know whether it's over or under, but it's closer, right? The only way to know for sure is to find the exact area. Yes, sir.
And the same way you could do this is to take the left and the right input.
Yeah, you could do the left sum, and then you could do the right sum, add them up and divide by 2, average left and right, yeah. So that's always true. The midpoint is always equal to half of the left sum plus the right sum. Right. In other words, average left and right sums. Yeah, and that gives you the same thing.
Yeah, but our own is always
All right, so I'm not gonna prove the whole in detail, the trapezoidal and Simpsons rule. I'm just gonna kind of state them with a little bit of explanation, and why we would bother using them. So this is a crude estimate, right? I only have 4 subintervals. We can calculate the exact answer, right? The exact answer would be the integral as x goes from 0 to 2 of x squared plus 1 dx. So let's see, what's that going to be?
1/3 x cubed plus x.
1/3 x cubed plus x evaluated from 0 to 2, which gives me 8/3 plus 2. So let's see, 8/3 is how many? It's 2 2/3. That's 4 2/3. Is that what you said?
8. Oh, I kept it in.
Oh, you were doing mixed
fraction.
number?
Yeah. No, I was doing fractions.
Improper fraction. Yeah.
Improper fraction.
I think it's 4 2/3. That sound right?
Yeah.
I like that way a lot better.
Yeah, no doubt.
Mr. Oya was always like.
But these are our humble beginnings.
Yeah, don't we just leave the past in the behind though?
Yeah.
Leave the past in the past. And we don't even need a final then.
Yeah.
No, we
I
do
just write a
not.
note that says you guys did great calculus.
Mhm.
Good
Yeah.
work. Good luck next quarter.
I think that's true.
I would cry.
You should really do that.
So our first estimate was a definite overestimate, right? We were more than 1 over, which is a pretty large relative percentage. Here, we're not too bad. 4.625 versus 4.6666666. All right, so here's the trapezoidal rule instead. Trapezoids. So a trapezoid is a 4-sided figure that has at least 1 pair of parallel sides. So a rectangle happens to be a special case of a trapezoid. The trapezoids we're going to be looking at are going to be these vertical suckers that have these 2 parallel sides, base that's perpendicular at the bottom, but we just connect the endpoints with align segments, and that gives us a trapezoid. Okay, so if we take the example we were just looking at, where we're going from 0 to 2, and let's do, so this would be what we're trying to find is the T4 estimate, the trapezoid 4 subintervals for our function. So 1, 2, 3, 4, 5. And so we have points at, let's see, 1 there, 0, 1, 1, 2, about there, 2, 5. We're in this vicinity, so we're heading up with our parabola. Bigger point, it's the line. And the difference here is it's kind of like a left or a right endpoint in that we want the height of each of our values, 0 included, 1/2, 1, 3/2. So remember, right endpoint uses the last 4 numbers in your interval. Left endpoint uses the first 4. Trapezoid's going to use every one of them from beginning to end. Because what I'm going to do is I'm just going to connect the dots with straight line segments. So since this function is concave up, each of these trapezoids is a little bigger than the actual area I'm finding. So this will be an upper sum, because each of them is a little bigger. What's the formula for a trapezoid? So often in a trapezoid, they call like this side base 1 and that side base 2. In these cases, those are my heights. And then I have this height in between there. So the formula for a trapezoid is average of base 1 and base 2 times whatever that distance across is. They usually call that the height of the trapezoid. I'm drawing sideways compared to where it's usually drawn. For us, what's that going to look like? Well, if we started at the beginning here, my first height would be f of 0. My second height would be f of 1. Cut those in half and then multiply by delta x. And that would be this area right there. This area right here, well, that would be f of, oops, no, what's my, sorry, 1/2 is my, I screwed that up.
Okay, I was confused.
I'm confusing I with the actual x value. So in this case, I'm going to have like 1/2 there. So this one's going to start off with f of 1/2.
Well, it wouldn't be right if you're, because you said heights, so technically you would.
I just go with it.
Okay.
So f of 1/2 plus f of 1 over 2 times delta x. That would be that one. Do one more, and you're going to see a pattern involved here. What's the area of that one? Well, wouldn't that be f of 1 plus f of 3/2? Whatever those happen to be, average them, multiply by delta x. So what ends up happening is f of 0 only got used once, but f of 1 was needed for that interval, and it was needed for that interval. It got used twice. The third function value, it was needed here and there. So pretty much all of the middle x values are needed twice. And the last two are only needed once each. So the general formula for trapezoids is going to look like this. So Tn, find your delta x. I'm just going to pull that out front. And then notice every one of these has a half in it. So I'm going to factor out a half too. So I'm going to factor out a delta x over 2. And then it's just f of x0 plus 2 f of x1s plus 2 f of x2s. And you just keep going on down the line all the way to the end. The last one is just going to be, that's f of xn or f of b. But right before that would be f of xn minus 1, and that one's needed twice. And that's the formula. And you get a way better answer than you get from the left endpoint, the right endpoint, or the midpoint.
X minus.
Yeah, so bottom line is the first function value gets used once, the last function value gets used once, and every other function value in between has to get used twice. Because they're both the left side and the right side of the trapezoids going in between.
That's n minus 1.
So this is an n minus 1 right here. Yeah, sorry, that's a little messy. I'm exceeding the resolution of my pen on the screen. N minus 1. Just right before the end. So that's the formula in general for trapezoids, and you're just going to get nicer answers out of it. Okay. So if we apply that to ours here and found T4, our delta x was a half, and we divide that by 2, we're going to get a fourth outside. The 0, plugging in 0, is just going to give me a y value of 1. The next y value is plugging in 1/2. 1/2 squared, 1/4 plus 1, 5/4. So I'm going to have 2 times 5/4 for the second one. The third one is going to be 2 times plug in 1. 1 squared is 1 plus 1 is 2. So 2 times 2 plus 2 times the next one. 3/2 squared. 9/4 plus 1. 13/4, right? Remember we did that one before? I'm going to have 13/4. And then I'm down to the last one, which doesn't get used twice. It's just 5 is that y value. So that should be a better approximation of this. I'm going to try typing that in a calculator quick. So I have 1/4 times 1 plus 5/4 times 2 plus 2 times 2 plus 13/4 times 2 plus 5. If I did that right, I get 19/4, which is 4.75. That is an overestimate. The actual answer is 4.66666. Yeah, so we're a little over. And that should be a little closer than the midpoint rule. All right, so I'm not going to do Simpsons Rule because I don't have time, but I'm just going to express the idea. What Simpsons Rule says is, someone said, was, just thinking about this, you have these functions at different heights. So maybe these are what my function are doing. 1, 2, 3, 4. Let's forget about this last one for a second. What someone was thinking was, well, instead of making straight line segments from here to there and there to there, what if instead we fit a parabola through those 3 points? And then we fit another parabola through those 3 points, however it fits. What you'll get is a tighter fit and less error as you find those parabolas. Carter's saying, man, that just does not sound fun. So setting it up is a pain in the butt, but once you get the general flow of it, it's wicked awesome and cool. So what ends up happening is you're going to get your delta x, but this time over 3, because you need 1, 2, 3 points to make it happen. And if you do the solve for the parameters of the parabola, each of these y values is needed, right? Multiple times each. And here's the pattern that breaks out. You're going to get an f of x0 plus, it's 4 or 2 next, I forgot. It is a 4. The next one gets used 4 times. The next one gets used 2 times. And it just keeps cycling 4, 2, 4, 2, 4, 2 till you get to the end. So let's see, my third one would get used 4 times, but then I'm at my 4th one here, and so that one just gets used once. A proof of that is it's an algebraic 3-pager, but it breaks down to this beautiful pattern. You just alternate 1, 4, 2, 4, 2, 4, 2, and then you get a 1 at the end. times the function value, and you just take delta x over 3, and that gives you a way tighter fit. So why do we care about these? Can we find an antiderivative for every function we come across? The answer is most of the functions out there actually don't have antiderivatives. Even though we have these huge tables of antiderivatives, there's way more functions out there that don't have antiderivatives. We've just scratched the surface on what we can do with calculus. It turns out we need these numerical techniques to come out with answers. And we need to be able to figure out how far off our answer is. And it turns out there's a whole nother thing you can do, and you can analyze the error. And you can estimate how far you are off from the real answer, even though you don't know the real answer. It's kind of bizarre.
So if you find the real answer using that?
No, but if you tell me, if you say, hey, I've got this project, I need to be within 1,000th of the actual answer, then I can pick the right n subintervals, and I can get you that. And then if later you come back and say, no, I was wrong, I need it to the nearest millionth, I just throw some more n's in there, and I can get that for you. The problem with that is for a big enough n, it can really grind the computer down trying to make that calculation. So people are always trying to come up with more efficient ways to make these calculations. Because in reality, most problems don't have a nice, neat antiderivative. They're messy. And we have to resort to computer technology to try and solve them. Okay. What did we do before computers? We tried to figure out what the real function was, realized that was too hard, so we tried to make an easier function that was close to it, and use that as an estimate, right? Which in this case, the idea of fitting parabolas to a complicated curve, because a parabola is a relatively easy shape to work with. And then someone else says, well, I'm going to fit cubics to it, okay? Which is doable too, and there's a whole nother pattern to that one right there. It's a wee bit more complicated. So, and what's that? I'm out of time.
Oh, I was just going
Oh. All right,
Yeah,
so Riemann sums, there's a ton of different kinds out there. The main one you need to know is a right-hand sum. There will be a question about a right-hand sum on a test. I'll have the take-home test ready by 5 o'clock today. That's the deadline I gave myself. I finished another 4 take-home exams last night. I think I have 4 to go. So I will definitely have this back tomorrow. You're not one of those 4. I didn't get to yours yet. Did I?
No. I'm saying I'm one of the 4.
Oh, you're one of the 4 I haven't gotten to yet.
I'm one of the 4.
I just got to yours last night. I finished yours like 11 o'clock last night.
Mine's not in though.
I didn't? Yeah, it is.
I did.